Hello friends, welcome to my channel. Let's have a look at problem 106, construct binary tree from in-order and post-order traversal. So in this video, we're going to share two formats of solutions based on recursion. So first, I'll read through the short statement of the problem, and then we do the analysis, and finally we share the code. So first, let's look at the statement. Given two integer arrays, in-order and post-order, where in-order is the in-order traversal of a binary tree, and post-order is the post-traversal of the same tree. So we are required to construct and return the binary tree. So here are two examples. So the example 2 is sort of trivial because it contains only one root node. So we just need to return the root node with value -1. So in example 1, so we notice that the root is 3, right? So which we can spot from the last element in the post-order traversal list or array. Then we can find so here this is the root, and then the left is the left subtree, and this is the right subtree in order traversals. So then we can get this is the left subtree and this is the right subtree. So this is the return. So we're going to give a refined analysis for example 1 in our analysis. So now let's look at the constraints. So the constraints, the first one specifies the problem size, and the second one basically is an consistency assumption. So here I'm going to emphasize the fourth one. In other words, the in-order and post-order consist of unique values. So this assumption actually is very important for the method we are going to share. So with that said or pointed, let's look at the analysis. So the method I'm going to write here is based on recursion. So the important assumption in this problem is that in-order and post-order consist of unique values. So this uniqueness of values are very important. So this assumption actually enables us to use root value, in other words, the last element in the post array, to find the in-order and post-order traversal arrays for the corresponding left and right subtrees. So the operation is actually straightforward. So we just compute the index of the root value. Due to the uniqueness of the values, so this index is a fixed one, right? So with that said, we can actually depict our procedure. So here I'm going to use example 1 to fix the idea in between. So we are going to separate this procedure into several steps. So step 0, so we first write a stop condition or base case for the recursion. So in other words, if this not is the in-order or corresponding post-order is an empty array, so we're going to return a null. So this is the null tree. So step 1 is that we construct the root node. So this is easy. Actually, we can find the root value from the post-order pop. So the last element corresponding to the root of the tree. So this is the root value. Once we get the root value, so we can construct the root node. So this is actually just a call of the class or the instantiation and tree node object. So in example 1, for example, the last value is 3. So it's corresponding to the tree node with value 3. So this is step 1. And then step 2 is to construct left and right subtrees recursively. So first, as we mentioned, we can get the index for the root value. So here is 3, so corresponding to index 3. So in the in-order traversal, left to this index is the in-order traversal for the left subtree, and to the right is the in-order traversal of the corresponding right subtree. So similarly, we can see, so once we get the in-order traversals for the left subtree, so we can get the corresponding traversals for the right. So this is very routine now. So for example, in example 1, so the left subtree in-order traversal corresponding to this none. This is the list. And the left post-order traversal is also corresponding to this one. So here I would first point this none and then point this none. So this is the left in order and left post order. So similarly, we can get the right in order and right post order. So this is the right subtree in order traversal corresponding to 15, 20, and 7. And so we can locate the positions in the post order. So this one. Notice that we have popped this 3. So we shouldn't include this 3. So, or another way you can inspect is that the in order and post order traversal for the tree or subtrees should have the same length. So this is step 2. So after we get this one and this one, so we can build the left subtree and the right subtree accordingly or recursively. So the last step is now trivial. So we can connect the root with the left subtree and the right subtree. So root left equals left. In other words, equals this part. And then the root right equals this one, or equals this part. And then we just need to return the root. So this is the analysis of the code, the method. So now let's do the code. So first, I'm going to write a version 1. So for this, I'm going to make it very verbose. So first, I'll write the stop condition. If not in order, so we can just use the in order. It's sufficient. So we're going to return now, or just a return. So this can be regarded as a stop condition or a base case. Next, we are going to get the root value. So root value is nothing but the post order pop. So once this done, here let me point out that this post order array is modified. So now let's construct the root. So the root equals tree node root value. So once this is done, so we want to find the corresponding right and left subtrees in order and post order traversals. I will get this index, that is in order index. So we're going to put the root value. Then left to this index is corresponding to the left subtree in order traversal, and then also we find the corresponding post order traversal. Then we build the root. Let's do it in one go. So root left. So will be a self call build trees. Then let's first find the in order traversal corresponding to the left subtree. So it's this part, right? And then post order traversal. So post order traversal is also up to this IDX corresponding to the left subtree. So notice that the in order and post order traversal should have the same length always, or empty simultaneously. So this is the root left. Then let's do the right. So self build right tree. So in order. So we're going to start from IDX plus 1 up to the end. Similarly for the post, IDX plus 1. So here should be let's see, post order. So it should be IDX, because so here we notice that up to the end we didn't include the 3, for example, in example 1, because we have already popped it. That's why we can write IDX up to the very end. So that's done. So we're going to return the root. So this is a one solution format. Let's do a test. Yeah, it passed the example we used for demonstration. Now let's do a generic case check. Yeah, it passes all the cases. It should be fast enough because yeah. So next, let me write another version. So I will copy the function signature here, and then I will put this one v1, just the 2. And then what we want to do is that we want to save some space. So for this, actually, I can make a map in order to recursively do this index check. So this is actually a static translation for the first version. So here, for this purpose, I'm going to use map in order. So this actually maps the corresponding root node to its index in the in order array. So here I'm going to use dictionary comprehension. So for value and I, for I and value in enumerate, so in order. So this way, we just need to look up in order, rather than call the index function. So then what we are going to do is that I'm going to write a builder function. So builder. So I'm going to accept two indices, low and high, and then we want to build. And in the finally, we're going to call this and return builder. So the index will be 0 and the last index. Let's see, I'm going to use in order, so -1. So that's the whole logic. So here, the bulk of the work is to do the translation from version v1 to here. So now for this, we still need, this is in fact, is still a recursion. So we need to have a stop condition. So for this format, actually the stop condition is still an empty in-order traversal or post-order traversal list. So this corresponds to if low is greater than high. So in this case, we're going to do the return now, or just the return. And then we're going to build the root. So let's use X maybe. So tree node. So post order pop. So corresponding to here, right? Root value. So and then so this X actually is already a root node. So let me write it as root to make a comparison with the v1. And next we're going to find the mid corresponding index, the map in order. So this actually corresponding to call the index function, but we change that to be a lookup table or dictionary. So this will be the root value, right? So then we are going to build the trees. But in this version, we need to first build the right subtree in order to avoid an empty list error. So for this, I'm going to do the root right. So we're going to call the builder function, and we're going to start from mid +1, and then high, right? So this is the right, and the root left. So this is also from the low to mid -1. So that way we finished building the tree. So we just need to return the root. So that's the logic. So what we are going to do is to call this function and do the return. So this is the second version of solutions. So now let's do a special case check first. Yeah, it passes a special case. Now let's do a generic case. Yeah, it passes all the generic cases. So I guess that's about it for these two versions of recursion solutions to the problem. So here I want to emphasize that. So in this problem, the assumption that in-order and post-order consist of unique values is essential. So with that said, I guess that's the end of this video. Thank you very much.